Hello everyone. In this video we are going to look at a multi-class classification demo in TensorFlow. And a simple example is always using the MNIST data. These are a bunch of training images that are for numbers 0 to 9, and they are all handwritten, and these are a bunch of images of size 28 by 28 pixels, and they are used to train they can be used to train any neural network or any machine learning system, and the goal is to tell you what kind of digits they are showing, right? Whether it's 0 all the way to 9. So you have a total of 10 classes, a class per digit from 0 to 9. And so if you give it any image again, it has to generate a number between 0 to 9. Now, how would you do that? So here we need TensorFlow and Matplotlib for plotting and for the TensorFlow thing. We also need some other libraries I'll show you. So the first thing you do, the MNIST data is already available under tf.keras, and under data sets. So it's already there. You don't need to download it. You can just get it, okay? And then this creates an object, and then you use the load data method, and that will give you xtrain and ytrain as well as xtest and ytest. So you see the data is even basically already split into training and testing. So you don't need to bring the whole data and then use that test train split command. Okay, and what is that? Well, if you look here, I ran it for you. You have 60,000 training images and 10,000 test images. Okay, now these images, as I said, they are 28 by 28, and when you import them, they are going to be integers from 0 to 255, from black to white. So the first thing we do, we divide all of the training images by 255. This way, the values of the pixels are going to be only between 0 to 1. Okay, and by dividing by 255, now they're going to have floats. So basically, this is what you do to convert those integers, unsigned integers, to floats between 0 to 1, okay? So this is what you do also in MATLAB as well. If you want to do it, you convert uint_a to double. Okay, and here you can print the shape of the xtrain and xtest, right? So if I run that for you, you can see that, as I said, 60,000 images of this size for training, 10,000 for testing, okay? Now we want to perform the multi-class classification. Since it's a multi-class, the activation function in the output layer should not provide only two numbers. It should provide a bunch of numbers, so a sigmoid cannot be used. And if you looked at my previous video on activation functions, you know that softmax is a function to provide such output. You can have as many outputs as you want, and some of it provides like a probability density distribution, where some of those numbers from all the output layers, all the output neurons, some of them will be 1, okay? And those numbers correspond to probabilities that this image is either 0 or 1 all the way to 9. So I get 10 numbers, some of them is 1, and the one that is the biggest number is most probably the correct class, which we'll see. So here we create a sequential neural network model. The first thing we need to do is, these images are matrices 28 by 28, okay? And they can even have colors in this case. Now you see in this case they don't. So they are just 28 by 28, okay? So they are already grayscale, that is good. So the first thing you do, you vectorize them into a line vector that is going to be 28 by 28, right? Which is like 700 something. And then you feed that vector into the neural network one by one, okay? So you have to because remember that in binary classification, the size of the input should be what? Should be n by d, where n is the number of samples you have and d is the number of features. So here, each feature that you have is one of the pixels. So by multiplying 28 by 28, you get the total number of pixels in each image, or the total number of features, and 60,000 is the number of samples, okay? So you want to convert this three-dimensional set into a two-dimensional, where 60,000 is the first dimension, the other dimension is 28 squared. So you use a flatten input layer to convert it into a vector. Then use a dense layer with as many neurons as you want. Here I go with 32. This guy is a hyperparameter and you can change it. And there is no specific reason that I went with 32. I mean, you can try smaller numbers or bigger numbers and see the result of that on the accuracy of the results. Okay, so you can do a search method that I mentioned under my machine learning videos for selecting hyperparameters. So here I tried 32 and that was good enough. You can use more neurons, but to me 32 did actually a pretty good job. And the activation function, this time I use a ReLU function. Then, to avoid overfitting, because I have a ton of neurons here, right, 32, or I can, as I said, I can have a lot more. I'm going to, and lots of weights and biases, I'm going to use this new feature called a dropout layer. What is a dropout layer? Here I provided the explanation for you from the website of TensorFlow. It says a dropout layer randomly sets the input units to 0 with the frequency of rate, and rate here is this number that you provide. So here with a frequency of 0.1 or with 10% probability, it is gonna what? It is gonna set one of the inputs, right, to 0, and at each time during the training, which helps prevent overfitting. Okay, so when you do that, this avoids the scenario where one or a few images are dominating the entire classification. So once in a while, it kind of ignores some of these input images and set the weights or biases of those neurons to 0, make them a dead neuron. And so by this way, it is avoiding the misclassifications and domination of the total classification by a few images. So this is one way that you can do a avoid overfitting. There are other ways, okay? You can use modified cost functions for generalization, and again I have videos for that under my machine learning playlist, where you can see the lasso and you can see the ridge and the other methods of machine learning where a punishment term, a penalty term for overfitting is added to, like the sum squared error or min squared error. Okay, so this is another way to avoid overfitting. So here I go and say 10% of the time, get rid of some of these inputs, set them to 0, and only use the other 90%. And this randomly changes. So it's not going to be the same neuron all the time. It is changing. And so this is, again, one way to avoid overfitting in dominance. And then for the final layer, which is also dense, I use 10 neurons. Why 10? Because I have 10 output classes, numbers from 0 to 10. And the activation function, as I said, has to be a softmax function. So this is my network. Then with the compile, I need to provide the optimizer. I can use Adam or anything else. Here I go with Adam. For loss function, I use the cross entropy, but not binary cross entropy, okay? I use what we call sparse categorical cross entropy. And what is that? Well, here, each one of these categories of the data, numbers 0 to 9, really, not 10, numbers 0 to 9 will be encoded using one hot encoding. Again, you can see one hot encoding in one of my videos, but basically you create 10 digits. Let's say if number is 5 and you want to do one hot encoding of that, then you say this is not 0, this is not 1, not 2, not 3, not 4. It is 5, no 6, no 7, no 8, no 9. So you see, you use 10 digits. You only set one of them to 1, the number that corresponds to this correct class. And this way you encode number 5 to be used in the entropy. And since out of these 10 digits, only one of them is 1 and the rest of them are 0, so we call it sparse. And this one hot encoding is used to encode these categories of the images. So that's the root for the word categorical. Okay, so here we use this loss function. And the metric is accuracy. So now that the system is ready, I pass to it the X train and the Y train to model fit. So it trains my network. And for validation data, I pass to it X test and Y test and a bunch of epochs. And here you don't need to pass a huge epoch. Actually, after 15 to 20 epochs, the change in the accuracy is bare minimum. So you don't really need to go a large number of epochs here. And it takes quite a bit of a time, okay? Each epoch here, if you run it, it is going to go through a ton of images, okay? It goes through lots of images, and it takes quite a bit of a time. You see, the first epoch was like 9 seconds or 3 milliseconds. And here I started with a loss of 0.42 and accuracy of 0.87. And as you go down through the epochs, you see that my loss function is now 0.09 and my accuracy is about 0.97, 97%, which is relatively good. Okay, and these are the values, the corresponding values for the data on the test function, the test loss and the test accuracy, val loss and val accuracy. So now that I got those after 20 epochs, I can plot them. So here is the plot for the loss function. You see it is going down, down, down. Still not completely flattened, but it's almost going to a straight line. For the test data, it's already at a flat plane here, maybe even increasing a little bit sometimes or oscillating. So really after this 17.5 epoch, you don't see much of change. And then you can look at the accuracy, right? So here is the accuracy, which is increasing on the training data, and after a while you see that it's not improving anymore. So this is the plot of the loss function and the accuracy. So now another way that you can look at the results is using what we call a confusion matrix. And in my video under playlist machine learning, under the 2 videos on prereqs and terminologies in machine learning, in one of them I talked about the confusion matrix. And confusion matrix basically shows you from the 0 to 10 digits, the numbers from 0 to 10, if the actual class is 0, how many times it has been predicted as 0, how many times it has been predicted as 1, all the way to 9. And then it repeats that for if it was really number 1, how many times it was detected as 0, 1, and 2, all the way to 9, and then goes down to if it was 9. So basically it is giving you the true positives, the false positives, the true negative, and false negative. And in order to do that, here I need to bring from scikit-learn metrics, I need to bring confusion matrix method as well as confusion matrix display. So what do? I pass the test data to my model predict, and I get Y prediction. Now this Y prediction is not going to be a single number like this image is 3 or this image is 5 or 6. It's just, remember, the softmax function is just a what? A vector of probabilities. So for each image, you get 10 numbers, and these are the chances that the image belongs to one of those 10 digits. But I really need a single number to compare it against my Y of the test. Y of the test are a single number. It says this image is 3, that image is 4, that image is 6. Y test is just a bunch of single integer numbers, while Y predict that I get out of here is for each image you have 10 numbers. So I need to find which one of them is the maximum, so I use the argmax command. And since it's a matrix, you have to tell it along which dimension you want the maximum, along the rows or along the columns. So here, by saying axis 1, I'm saying along the rows, because this Y prediction is going to be basically 10,000 by 10, 10,000 test images, and each one has 10. So I say go along each row, get the maximum, which is basically per image. And so now this guy is just going to be 10,000 by 1, and I convert it into an array of NumPy. Even I can show you some of the results here, and then I pass the true labels and the predicted labels to confusion matrix to create this confusion object, and then I pass it to the confusion matrix display.plot to plot it for me. So let's go ahead and show you. There we go. You see here, look at this. So this is what's now, these are the first 10 or 11 values in the Y prediction. You see now they are only a single number. It says, hey, the first image in the testing set belongs, it's predicted to be number 7. The second one is 2. The third one is 1. The next one is 0, and so on and so forth, right? And this is the confusion matrix, which is very good to see. It says, hey, if the true label was 0 out of all the times that we tried it, 900, so this is, I assume this is, let's see, because the total of all these numbers in this table is 10,000, okay? So out of the number of images that were truly 0, 970 times we truly and correctly predicted 0. 3 times, or sorry, here, 4 times we predicted to be 6. 2 times we predicted a 0 to be a 7. 3 times 8, 1 times 9, and we never predicted it to be 1, 2, 3, 4, or 5. Okay? If the number was 1, then 1123 times we correctly predicted it as 1, 2 times we predicted as 2, 1 times we predicted as 3, and so on and so forth. So the true positives are the diagonal numbers. And if these numbers are much, much bigger than the rest of the numbers, that means you did a good job, because the rest of the numbers are false positives and true negatives. Okay, these off diagonal numbers. So they should be very small, and you see they are. Okay, so that is the confusion matrix on the test data. And remember the accuracy for the test data, it was about 97%, 9684, which is really good. And you can see that here as well. Now, if you want to create an image yourself in anywhere like Paint, or read it from internet or something, upload it and then apply this train network on it to see what kind of number that is. Here is the part you can do. So here I use the Python imaging library, PIL. I import it. And I also bring in IPython display to display the image, because I want to show you the image that I'm reading in. Okay, so that I have a few images here, a few small images, black and white. And here, what do? The first thing is use pill.image.open to open that image. You have to pass to it the name of the image. So here I'm reading number 4. Then convert L. What does it mean? It means convert it to grayscale. If that image is color image, convert it to only grayscale. And then make sure you resize it down to 28 by 28 because the image might be a little bit bigger or smaller than the MNIST size. And this network is only trained on 28 by 28 and on grayscale images, so you have to do these conversions. So you bring it in, convert it to grayscale, resize it, okay? And the other thing you might want to do is to invert it. Invert means make the whites black and make the blacks white. Okay, because the images I have, the background is white and the number is written in black. Here, I convert the number into white and the background as black to more kind of correspond to MNIST. I can use this display that I imported from IPython display to show you the image because I want you to see the image I created. And then this image I bring in using this PIL library is not a NumPy array. So first I convert it into a NumPy array. Then the numbers are between 0 to 255. So I divide it by 255. So it goes to 0 to 1. Then I reshape it into 1 by 784. What is 784? That's 28 times 28. So I flatten that image myself. And then I pass that flattened or vectorized version of the image to model.predict to give me a class. I can see that class here. Now it's not going to be again a single number. It's going to be a vector of 10 numbers. So I need to see which one of them is maximum. And then what? I show you that maximum class. So let's go ahead and run that. That's your image. You see that's number 4. This is the output for it, and clearly the maximum number in this vector is this guy here, which is this is 0, this is 1, this is 2, this is 3, and this is what? 4. So the prediction for that number is 4, and the digit is actually what? 4. So it is doing a good job. Now it doesn't mean whatever number that you bring in, it is gonna do a perfect job, okay? So here, just to show you, if I bring in 2 instead of 4, look what happens. So here I use the other image I created, image with digit 2 in it instead of 4. See if it does a good job. You see it does. Okay, 2 it does another good job. You see it classified it properly. What about 8? So here, and these I handwritten myself. These are not MNIST numbers. Okay, let's look at 8. You see 8, it messed it up. Look. It think that the number is 2, although the number I created was 8, but you see it does think it as 2, and probably the reason is this is too thin for it. Okay, so if I made it thick and change the shape of it, probably it would do a good job on it too, but again, it's not always 100%. Okay, there is some misclassifications. So this is what I had to show you right now, and I'm going to upload for you this file as well as this digit2.png, so you can play with this and learn from this. Okay, you can create your own image and basically try it here, or you can use a different number of neurons. You can try different activation functions for this one. For this last one, do not change it. Do not change this 10. Do not change the softmax. If it's on MNIST, if it's on something else, feel free to do so. But if it's on MNIST, don't do that. You might try to change the number of the probability of dropping out and see if it improves or not improve any final results. So thank you so much for your attention. I'll see you in the next video.